I'm going to start off my today's session officially. And first of all, let me share the screen where we have to, first of all, see what is the status of our syllabus, because that is also very important. And if I go through the syllabus, if I scan the syllabus, I will find that we are in Unit 6, and we have done the test of single mean for small sample, test of difference of means for small sample, a test of correlation coefficient has also been done by using statistic, and chi-square test for goodness of fit and independence of attributes have been done. I have spent maximum amount of time in discussing chi-square test. Only one thing is remaining. It is called the test for ratio of variances. My today's discussion is this one. I am going to discuss about test for ratio of variances. Now you probably were happy that we are almost done with the syllabus, but you shouldn't, because one particular portion is still left out, and I have not discussed in details about this, which is this particular section, Unit 3, bivariate distribution. And I very well remember that once I was presenting a particular note on bivariate chart, and there I was explaining a problem, and one of the students named Nikita, she raised a question, and I just uh, avoided answering that. Later, I didn't go back to that section. Probably you are thinking that I have forgotten, but I have not forgotten, because that very moment I decided to discuss bivariate distribution in detail later on, once I complete my hypothesis testing process. Because there is always a trouble in dealing with continuum probability, in where things happen in continuum probability. So I leave this section for my last part of discussion of this particular syllabus. One another thing I must declare is that once I complete the syllabus as a whole, it doesn't mean that we have discussed everything in it. There are some gaps in the syllabus which have not been mentioned, and there is no provision of discussing the things like there is nothing mentioned like we have about the estimation of parameter. This is a very important chapter in statistical theory, and nothing is mentioned related to how different samplings are done. So sampling theory is also not there in our syllabus. So these two topics are the gaps of the syllabus. And this is not the end of the syllabus. After that, there comes parameter. This all these testings that I have done, like Z test, T test, chi-square test, F test, that I'm going to do right now. All these testings are parametric testing. There is another kind of testing which is called non-parametric testing, where the population parameters are not known. But non-parametric testing discussion is beyond the scope of the syllabus, so I'm not going to discuss it. If you find any question in the previous question papers of WBT, like in the name of sign test, rank sum test, or like Kolmogorov-Smirnov test, if you find any such questions over there, you just immediately inform me, then I'm going to discuss those parts. Otherwise, as per the syllabus, topics of the syllabus, I cannot find a non-parametric test is there. So I'm not going to discuss this section. And apart from these, other topics are there, like statistical quality control is there, design of experiment is there, principal component analysis is there. Principal component analysis is very important topic, which contains in it analysis like factor analysis, cluster analysis, discriminant analysis, which are essential for learning to know about machine learning, and analysis of variance and its various types are available, which are also part of this statistics course. And then there is multivariate statistics. All these subjects are there, but these are beyond the scope of this particular course curriculum, which is meant actually for beginners. And when I talk about the analysis of variance test, remember that in analysis of variance test, this particular test for ratio of variances, which I'm going to explain right now, is it plays a very fundamental role. So if you do not understand the test for ratio of variances, you will not be able to understand analysis of variance, because in analysis of variance, test of ratio of variances are actually calculated. So therefore, I'm going to discuss this part in today's class. I have not prepared any, I have not typed any thing about F statistic. I have not prepared any note, so that's why I'm unable to present anything, because preparation or typing things in uh, Word is takes a lot of amount of time, because we have to deal with lots of mathematical expressions. So I'll do that part, and once I do, then I can share the thing with you. But right now I do not have any presentation, so we have to rely on board work. Okay, so we begin with, there are two aspects that needs to be discussed. One aspect is the definition of F distribution, on the basis of which we need to do the F statistic. And there is F test, which actually tests the hypothesis. We shall try to do this part first of all, okay? Because we are in the domain of hypothesis testing, so we'll try to learn how and why this test is important and relevant. What happens is that, suppose we have two populations. So this is population 1 and this is population 2. Okay, or you can have a big population of this size. We can break it into two halves. This may be the population of men and this may be the population of women, and so on. We are drawing a sample from this population. So this is my sample S1 from population P1, and this is my sample S2 from population P2. Or if you are talking about this aspect, suppose we are drawing a population from, we are drawing a sample from this population PM, which is SM, and we are drawing a sample from this population PW, which is SW. So in various ways, these samples can be drawn from the population. Now, every population, since we are doing the parametric testing, every population is following some sort of probability distribution. Here we shall assume, our assumption is that our population is following normal distribution. Okay, with this assumption, I am trying to draw the samples from these two populations. Now, if someone asks that, okay, since this population is following normal distribution, so it must have a population mean and it must have a population variance. So, and suppose no information about mean is there, no info about mean is present. But we at least know that this population P1 has a variance which we denote by, say, sigma 1 square, and population P2 has a variance which we denote by sigma 2 square. If I assume that if I design my null hypothesis in the following manner, that these two population variances, sigma 1 square and sigma 2 square, they are same. So if I draw the sample, their variance will be same. Population variance, the deviation of the points from some mean, will be similar for both the populations. So if my null hypothesis is like this against my alternative hypothesis that they are not same, question is, how can we test it? How can we test it? And what is the testing process? What is the testing process? So under this null hypothesis, the statistical tool that we use is known as F statistic. F statistic, and it is defined by Sx square divided by Sy square, or you can write S1 square by S2 square, where S1 S or Sx, these are the sample variances of first sample, and Sy or S2 sample variances of second sample. Okay, and to calculate this S1 square, you always remember that we need to divide by 1 by n minus 1, and we have to consider this summation xi minus x bar whole square for all the points, all the sample points. And for calculation of S2 square, we need to divide by, okay, I'm considering this sample size as n1, sample size of the first sample, and for the second one I have to divide by n2 minus 1, the sample size of the second sample, and we need to consider this square of the deviation, sum of the square of the deviation. It will be from I to n1, this will be from j to n2, and we have to consider yj minus y bar whole square, where x bar and y bar are means of first and second sample. But there is a catch. The catch is this: when we are going to implement this formula to test the hypothesis that population variances are same or not, we need to take care of one aspect, and which is as follows. We are going to use the formula S1 squared by S2 squared only when your variance S1 squared is greater than S2 squared. But if your variance S2 squared is greater than S1 squared, your formula of F will change its shape. It will be S2 squared by S1 squared. So this important point you have to keep in mind. So we will interchange between the two formula by looking at the variance of the thing. If the variance is larger, the larger variance will always be in the numerator, the smaller variance will always be in the denominator. So this is how we actually calculate the this F statistic, this F test statistic. And another aspect that which is very important is that since we are dividing to calculate the variance, since we are dividing this by we are multiplying by this quantity 1 by n1 minus 1, and we are multiplying by this quantity 1 by n2 minus 1. So degree of freedom here in this case of F test will be two-phase. Previously we used to apply only one degree of freedom, like kind of this we used to say that chi-square degree of freedom is n minus 1 or r minus 1 into s minus 1. T test has a degree of freedom like n minus 1 and so and so. But here we'll consider the F test corresponding to the degree of freedom which comes in pair. So we'll write the degree of freedom as follows. Degree of freedom in this case is n1 minus 1 comma n2 minus 1. So this is all about the F test which we are going to use over here. Okay, and if I look at the statistical chart, you will find that this is the probability. These probabilities have been calculated, and we have this F statistic for, we have this F statistic for 5% level of significance. Here on the left, you can see that degrees of freedom of the first sample is shown, and here on the top, the degree of freedom on the second sample is shown. And if you want to look for the tabulated value of F for say 4.9 degree of freedom, then we will first locate 4 on the leftmost column, and we'll locate 9 on the topmost column, and corresponding to that we will move in from left to right, and we'll hit at this point, which is 6. So this will be the tabulated value at 5% level of significance for degree of freedom 4.9. So that is how we try to locate the tabulated value from the F table. It is also available with you because I have provided all the statistical chart in the Google Classroom. This is another, they have calculated, they have started taking the degree of freedom from 1 till they go up to 120. And here you see that this particular table, here it is written, the table has been continued from the previous page, but here they have mentioned the term 95th percentile, and you know that 95th percentile and 5% level, they are same thing. 95th percentile is a complementary to 5% level of significance. 5% level of significance is complementary to 95th percentile. And this is not the end. They have also provided the F statistic table for 90th percentile or 10% level of significance. So you can take the help of this chart if you want also. They have also provided F test for 99th percentile and 1% level of significance. So F chart is quite huge. Okay, so you can take the F chart, any of this chart for your calculation. Okay. So now let's go back to our board work and let's try to solve a problem with the help of this test statistic. You be ready with your pen and paper, and if you want, you can do the calculation. So the question is, my first question of today's class is, in one sample of 8 observations, the sum of the squares of deviations of the sample values from the sample mean was 84.4, and in the other sample of 10 observations, it was 102.6. Test whether this difference is significant. Test whether this difference is significant at 5% level, given that the 5% point of F for 7, 9, degrees of freedom is 3.29. So how to solve this particular problem? Uh, you can make the problem complicated. We can be provided with the data values from which we can calculate the sum of the squares of the deviations, but here we don't have to do this because sum of the squares of the deviation is also already provided. They have calculated this thing for us, which is 84.4, and this happens for the observation 8. So this is my sample size, first sample. I'm considering this to be my first sample, which is n1, and I'm considering this to be my second sample, which is n2, but there is no hard and fast rule which sample you are considering to be the first or second. It is up to your choice. And for the other sample, the sum of the squares of deviations is given to be 102.6. So what we need to do, we have to, first of all, you have to design your null hypothesis. So your null hypothesis is fixed. We are actually testing the equality of the two population variances from which the samples have been drawn of different sizes, and against the null hypothesis that the same population variance are not same. Now we have to calculate the S1 square, which is the sample variance, and you know the formula is 1 by n1 minus 1 summation xi minus x bar whole square over I. Now this summation is given to you, which is 84.4, because this is my S1, sorry, this is my sum of squares of deviation is given to be 84.4, and my sample size n1 is 8. So we are going to substitute this thing over here, and if I do this calculation, we will find the value to be 12.0571. For accuracy, I'm keeping 4 decimal places after four digits after the decimal places. Similarly, S2 square can be calculated by using the formula n2 minus 1 summation over j yj minus y bar whole square. Here, this deviation is given to be yj minus y bar whole square. This deviation is given to be 102.6, and your sample size is 10. So we are going to apply these values over here. So it is 10 minus 1, and we are going to multiply this by 102.6. So if I do so, the outcome is 102.6 by 9, which gives me 11.4, 11.400, if I'm not wrong. Now, after this, what I need to do, this is my step 1. So let me write. My step 1 is to define the null hypothesis, of course. My step 2 is to calculate the things which I need. My step 3 is to find out which variance is greater. Okay, so we see from the calculation of step 2 that S1 square is greater than S2 square. Okay, this is my observation from the calculation. This is my observation from the calculation. So if it is so, we need to apply the F test statistic, which is S1 square by S2 square. It will follow F distribution for the degree of freedom 8 minus 1 and 10 minus 1. Okay, and that's why 8 minus 1 is 7 and 10 minus 1 is 9. That's why the tabulated value for 7, 9 degree of freedom is given. But if you do a mistake over there, if you do a mistake at this point, what will happen? If you do it wrongly, then you may get the tabulated value of F at 9, 7 degree of freedom also. It is also available. But this will not work because we are not testing at 9, 7 degree of freedom. We are testing at 7, 9 degree of freedom. And the deciding factor is this one. This is the deciding factor. Now the tabulated value is already given to us. We can check the tabulated value indeed for with respect to our table, the chart we have. So since that we have the chart, let us check whether this tabulated value is correct or wrong, first of all. So I'm stopping the share. I'm going back to the chart which we have with us. Now we are supposed to test the statistic at 5% level of significance. So if I consider this chart, then we have to go to the first table that I presented. This means this one, and it is the table for 95th percentile or 5% level of significance, and you have to hit at the 0.7 and you have to hit at the 0.9 on the top. And if I move on like this, you will find that the value is coming out as 3.68. The given value is at 7.9 degree of freedom. The given value is 3.68. The given value is 3.68. Okay, so okay, at 5% level, I don't know why they have provided this value. Somewhere maybe this is a mistake from their end, because from the book from which I'm collecting the problems, they have several printing mistakes. Actual value according to the, that's why I wanted to verify the tabulated value. So I shouldn't consider this one. I am trying to rectify this. The actual tabulated value that I have observed from the available statistical chart is 3.68. Anyways, so we have got our actual tabulated value. Now, since we need to consider this formula, this is our formula. So next, step number 4 is to do the calculation. Step number 4 is the calculation. So we are going to substitute the value of S1 square first on the top, which is 12.0571, and we are going to put S2 square in the bottom, which is 11.4000. And if I divide this ratio, if I divide one by the other, you will get it is 1.05, approximately equal to 1.05764. This is the result which is coming, and we see your step number 5 is the comment section. So in the comment section, what you are finding that your calculated value of f at 7.9 degree of freedom is lesser than the tabulated value of f at 7.9 degree of freedom, and therefore your conclusion is there is no significant difference between population variances. There is no significant difference between the population variances. I'm activating the chat box. I have activated the chat box. Please mention your roll numbers over there. And let me now talk about the F distribution, because your F statistic is actually following the F distribution. So how does this F distribution look like? Now the definition of F distribution is as follows. If capital X and capital Y are two independent This word is important, and there is a catch once again. Independent chi-square variate. Two independent chi-square variates with n1 and n2 degree of freedom respectively, then F statistic is defined by x by n1 and y by n2. So this is the formula. This is the definition of the F statistic. But the important part is that if you have noticed, when we defined the chi-square variate, we took the help of the standard normal variate. I told you that chi-square variate is the square of the standard normal variate. And when we are defining the F variate, we are taking the help of chi-square variates. F variate is the ratio of two chi-square variates. So all these things are interconnected to one another. And since chi-square variate is related to standard normal variate, so this is one of the reasons for which we say the population from which the samples are drawn in case of F test, they must be normal with having some parameters, of course. And this F distribution is a continuous probability distribution, and it must have a PDF. Okay, and the form of the PDF is actually a bit complicated, although I'm writing over here. So the PDF of this F distribution is like this. So we consider n1 by n2 to the power n1 by 2, and beta of n1 by 2 and n2 by 2. You probably remember the function beta mn. It is called the beta function. So this function has been used over here, and we get f to the power n1 by 2 minus 1 by 1 plus n1 by n2 f whole thing to the power n1 plus n2 by 2, where the variable f will lie between 0 and infinity. It's a real number. So it's a too complicated expression. And you see, whenever we want to calculate the p-value, whenever we say that, yeah, this is the p-value. So what is actually we're saying over there is that we have to integrate this probability density function from some lower limit to some upper limit, and we can repeat the process several times to get our p-value. I have explained this particular section on the basis of which statistical software's algorithm are written in my video 5 of chi-square test. You can watch the video. I'm again referring that video to you. This video is very important. I'm referring to you to go through the video carefully. You go through all the chi-square videos carefully, you will understand many aspects of statistical hypothesis problem. Now, this as now we have defined the F distribution and F test, and I have shown you how to apply implement this F test to do the problems, and it is a very simple problem that we have considered over here. Next part that is coming to your mind is, can we do the F distribution with the help of any mathematical software? Because you have already tested, just like the tiger tests blood, you have already tested the blood of statistical software. So we are always on the hunt of finding any such option by which we can ease our situation of, and we can get rid of doing these tedious calculations. So the answer is yes, we can do the entire calculation by using the Maple, and which I'm going to show you in the next session. So just wait for it.